we present Zeebra, a compiler for a low-level language with IFC. This work is based on Christoffer and Jon's master's thesis, which was advised by Aslan Askarov. Zeebra is an LLVM-backed compiler for C, a low-level language with information flow control.
C allows for type stack introspection at runtime. Consider the function f that takes an integer x as argument. On the stack, x will be located within f's stack frame. Say we wanted to change x. So how would one go about changing x? We can of course change it directly by assignment, but if we have indirection and know the stack frame, we can change it indirectly. Using C's fp expression, we can obtain a pointer to the current stack frame. Inside f, this will point to f's stack frame. This includes the security labels of the values located there. Using C's pattern matching on types, we can match the type of the arguments. Here we attempt a match on a single argument typed as an integer labeled age. This pattern matches the arguments of f. By indexing into the frame pointer, we can indirectly change the value of x. Stack introspection like this allows us to write programs that can traverse the stack and make modifications based on the types of the individual stack frames. C possesses the same constraints as other IFC languages. High branches only allow high side effects, for example assignments to high variables. Where C differs from the rest of the IFC crowd is that C does not allow implicit PC casting. Rather, the PC must be explicitly raised by an add command. Conditions on if expressions must flow to the PC. This provides mitigation against timing attacks by also having a timeout. If the internal command finishes before the specified deadline, the process sleeps until the timeout is reached. If the command finishes after the deadline, the program crashes to avoid leaking information. In this example, without the padding, the secret could easily be determined from the timing of the if command. The add command prevents an adversary from learning anything after observing the execution time of the high context. Either the command finishes on time or the program crashes.
Side effect-free operations on high variables generally do not require raising the PC. This allows some operations, such as arithmetic, to be performed at a low PC. This is because we usually assume that these operations are performed in constant time. That is, the label of the result is raised to indicate the flow of information, but no information about the operand can leak through timing side channels. However, on some CPUs, the timing of these operations are dependent on the operands, making our assumption incorrect. What can we do to mitigate this? Well, we can require that the PC label is raised. This mitigates the timing issue by employing the time padding of the add command. This introduces high delays to the code, however, but it will be constant time. Or we can produce slower IR code in these contexts that is guaranteed to be constant time. This makes code reuse harder, timing becomes a context-sensitive matter, which does not mix well with add commands. Or we can take the extreme option of disallowing the operation in the language entirely. This is not feasible to do for basic operations such as multiplication, of course, but it may be an option for more complex operations such as ternary operators. To avoid dereferencing dangling pointers, Zeebra uses a lock and key scheme. Every pointer dereference is accompanied by a version check. This version check must be done in constant time. For example, when dereferencing this high pointer to an allocation in the medium partition, the time taken must be independent of both the pointer and the partition. In Zeebra, heap pointers are represented as three tuples of 2 pointers and a version. The first pointer points to the actual allocation. Storing the version in band with the allocation would be dangerous, so it is stored separately in an allocation pointed to by the second pointer. If the versions are identical, the pointer is valid. If the versions are different, the pointer is invalid. The allocation and version node is either unused or has been reused. In this case, the runtime will deliberately crash. Having the second pointer allows version checking to be performed in constant time, as is required.
Runtime checking has an impact on performance. When benchmarking Zeebra on an AES example, we found that it ran 7 times slower than a C implementation. This is due both to the runtime checking itself and because the checking prevents LLVM from performing optimizations on the generated code.
To read more about Zeebra and C in general, visit our website linked here. We also have an interactive web demonstration of Zeebra where you can try it yourself. Thanks for watching.